Ball A is initially 250 meters to the left of the origin and ball B is 200 meters below the origin. A and B move towards the origin, while ball A moves to the right with a uniform speed of 20 meters per second. Ball B moves upwards with a speed of 10 meters per second. And we have to find the closest distance between the two balls A and B, and also the time required for them to be in that position. Let's take a snapshot of A and B in some arbitrary position along the way. Let's say that we took the snapshot after a time of t seconds. Point A is 250 meters to the left of O. So considering the signs, we take the initial displacement of A as minus 250 meters. Similarly, point B is 200 meters below the origin, so we take the initial displacement of B as minus 200 meters. The displacement of ball A after t seconds would be minus 250 plus 20t, since it moves to the right with a speed of 20 meters per second. Similarly, the displacement of ball B would be minus 200 plus 10t. The tan of the angle theta would be OY over OX. Now let's compute the velocity of approach. So we will take the components of VA and VB along the line joining A and B. And since we are computing the velocity of approach, we will consider components along the line AB. If we take VA cos theta as the positive direction, then VB sin theta will be in the opposite or negative direction. Therefore, the velocity of approach will be the relative velocity of the components, which would be VA cos theta plus VB sin theta. Now let's use the velocity of approach to find the minimum distance between the red and blue balls. In the previous lesson, we learnt the concept that when the distance between two objects decreases and then increases, at some point the velocity of approach must become zero. So VA cos of theta plus VB sin of theta at some point would be zero, and from here we get tan of theta as minus 20 over 10 as our second equation. We must preserve the signs here because we don't really know if this minimum distance condition will occur in the third quadrant or in the fourth quadrant. From equations 1 and 2, by eliminating tan of theta, we obtain the time as 14 seconds. So it takes 14 seconds for the balls to reach the minimum distance condition. You can see that the blue ball has already crossed over to the positive side of the x-axis, whereas the red ball continues to be on the negative side of the y-axis. Now if B was stationary and A was moving to the right, then we can say that the minimum distance condition would occur when A was vertically above B. But here both are moving, and that too with different speeds, so we cannot make that prediction in this case. Now let's find the minimum distance or the distance xy. Substituting 14 for t, we obtain OX as a positive 30 meters, which means it lies to the right of the y-axis. And OY is minus 60 meters, so it continues to lie below the x-axis at the time when the distance is the minimum. The distance xy would be the square root of 30 squared plus 60 squared, and that is 67.08 meters. This is the least distance between the red and blue balls, and at this point the velocity of approach is 0. To the left of this point, the relative velocity of the components would be the velocity of approach, and to the right of this point, the relative velocity of the components would be the velocity of separation. So the velocity of approach would turn into the velocity of separation beyond the point of minimum separation.